2-1 earthquakes. This is what I call the shake, rattle, and roll. Now I'll give extra credit points for anybody who can look up what that reference is. I'll give you a hint. It's from like the 1950s, 60s rock and roll era. Talk to Mr. Gar, I'm sure he can help you. All right, so what is an earthquake? An earthquake is when the earth shakes or rattles. And it often occurs because there's a sudden shift of the earth along a fault line. Now we talked about the different types of faults, and so you want to remember what we were talking about there. But you have a sudden shift across those, not the really slow ones, but the sudden ones, those cause our earthquakes. Now when that happens, a lot of energy just explodes out of that shift. It's going to travel out in all directions. Now, if this shift happens underwater, if we have this earthquake, okay, happens underwater, that energy, when it travels out, it's going to go into large, large waves. And, of course, that ends up in a tsunami. And so here's this little guy trying to run, because tsunamis are huge. They can be as tall as buildings, and they're just devastating. Now, a tsunami, it starts out by, if we're out in the sea, we have this big, long wave, all of this energy. But when it starts getting into the land, it starts to trip over itself. So the front part of the wave starts slowing down because of the land, and it pushes water back up into the wave. And so the wave kind of shortens a little bit and gets a little taller. And then as it keeps going, it keeps shortening and getting taller and shortening and getting taller until it's so tall it can't stand anymore, and it falls right onto the people. Oh, I should have drawn little houses and stuff here. There would have been tiny little houses. Oh, here's one. Doop, and there's another one. And there's another one. And there's a tree. I mean, these things are huge. They just wipe everything out. All right. Enough about tsunamis. Earthquakes, when they occur due to a fault, they're going to have what is called a focus. And this is the very single point where the earth first breaks. Okay? And the epicenter, that's the land above the focus. And that's where the worst of the shaking is going to occur. That's where the most energy is going to be, spent out. And then we're going to, this is the big shakes. Okay. So then when this focus, when there's a break over a focus, and we have an epicenter of an earthquake, there are three types of waves, and all three of them are called seismic waves. Okay, that's just because it's from an earthquake. They have primary waves, we call those P waves. Don't laugh, they really are called that. We have secondary waves, which are called S waves. And then we have surface waves, which are called L waves. But you can think of these as the land waves. So L, surface, land, L. And the P waves, these guys are going to follow through, they're going to travel through solids, liquids, and gases. They're going to go faster when we got dense materials. So think about that. What does that mean when it goes down into the mantle that's nice and dense? These are push-pull waves. Okay, I hate that. That's what your book calls them, so I'm going to tell you they're push-pull waves. The word we want to use, though, is longitudinal. And a longitudinal wave, that's where you've got a wave and it goes squish, 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 and it just moves along. What I want you to do, because they are much better artists than I'm a terrible artist, look on page 35 in your book. There's this beautiful picture that they made of P waves, S waves, and L waves. Study that. Now, S waves are slower than P waves. P waves are the fastest, right? And if anybody's ever had to really go pee, you know how fast you move to the bathroom. So the P waves are the fastest. The S waves, these are slower. These are often what we call the aftershocks. Now, S waves, they'll only move in a solid. They will not move in liquid. They do not move in air. So let me ask then, I want you to think, what do you think happens to these S waves when they reach the mantle? The hint there is, what state is the mantle in? Is it solid, liquid, or gas? And then we have the L waves. These are ones that are going to be on the surface of the land. Okay? These are the ones that do the most damage. They're the slowest of the three types. So if you have an earthquake, you're going to be able to see that there's P waves and S waves coming along long before, well, relatively, before the L waves hit the area. And this is the damage. These are the slowest types, but these are, here's another word, see I did it in black again, transverse waves. These are the waves that you see at the beach. If you stand there and you look at the water and it looks like this, those are transverse waves. So imagine that this is land and it was flat, and all of a sudden the L wave comes through, and all of a sudden the land is doing this just like the surface of the water. You can imagine why this would cause so much destruction. Anything built or living right there is thrown way high up and way down and shaken left and right and just broken all to pieces. That's also why places that have a lot of earthquakes, their building codes, they require that their buildings can move a certain amount of space left, right, up, and down without falling down. And it's because these L waves come and move the land in all different areas. Now we measure the strength of the earthquake using what is called a seismograph. Again, I want you to look at page 37 in your book. There's a nice picture of one. Now with a seismograph, the pen is going to be held still, but and it's held still with a weight, and you'll see that on the picture. And the paper though, which is on a roll, if the earth moves, the paper moves. But because the pen's on a weight, the pen stays still. So if the paper is moving beneath the pen, then you start getting little squiggles. So if there's no activity, you end up with a nice straight line. If you start having movements, then instead of having a nice straight line going across, you have squiggle, 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 squiggle. And that's what you see on the videos or movies when you see earthquakes occurring. Now, the picture that is made is the seismogram. So the seismograph is the instrument that you use. The seismogram is the picture that it makes, and it shows the strength of the earthquake. And a seismologist is a scientist that studies earthquakes. So they look at these seismograms. And one common scale, we're going to look at another one, at least one more. One common scale for measuring these is the Richter scale. And that's what you hear on the news when you have a earthquake and they say it was 5.3 on the Richter scale. The Richter scale starts at 0, but that means nothing. Really, if you have an earthquake, you can have a low, small earthquake, and that would be a Richter scale of 1. You're not going to feel that whole much. There may be a little shaking, up to a level 10, which is devastating. So if you have a low 1, and then comes along one that is 2 on the Richter scale, this is more than just 1 unit away. This is 10 times stronger. So every time you go up a number on the Richter scale, it becomes 10 times stronger. So 2 is 10 times stronger than 1, and 3 would be 10 times stronger than 2, which is why by the time you get to 10, level 10, you are just absolute devastation. Now, earthquakes are tricky because they are really hard to predict. There are people who think that they know how to predict them, and at the moment, the best scientists can do is predict within a couple of hours or a day. But think about what would it be like if they could predict years in advance and say, this is where the earthquake's going to be. Would you build your house there if someone could tell you there was going to be an earthquake? I don't think so. So that's the end of section 2.1. We will have 2.2 up momentarily.